Greetings, pre-calculus students, to another lesson in our unit on sequences. In our previous lesson, we talked about this idea of recursive sequences, and the lesson before that, I introduced you all to this idea of an explicit formula. So now we're going to look at a specific type of sequence. We're going to look at a specific type of sequence, an arithmetic one, to be more specific. But really quickly, these are the solutions to the bell ringer. If they were not covered in class, these would be it. So for number 1, 6, 12, 24, and 48 would be the remaining 5 terms. And for number 2, a sub 1 is equal to 4, and then a sub n is equal to a sub n minus 1 plus 5. Okay, so let's get to the lesson. So quick recap. A recursive sequence, or a sequence that is defined recursively, which we learned in our most recent lesson, is a formula that relates each term to previous terms, all right? So given the previous term, what do we do to that term to arrive at the next term? So that's what we do, or that is how a recursive formula is structured. All right, so let's look at a couple of examples here to get into this idea of what exactly is an arithmetic sequence. All right, so here we have 3 sequences. 7, 11, 15, 19, 2, negative 3, negative 8, negative 13, and 1, 5/4, 3/2, and 7/4. Now, each of these sequences, they do have something in common. So I'll wait a few seconds, see if you can figure out really quickly, what do these have in common? What do these have in common? You can pause the video if you want, but one easy way to see what they have in common is to quickly see what are the patterns. So first, let's see if we can establish some kind of patterns for each of these. Now, typically, the easiest way to establish a pattern is to check out the differences. See how much do the numbers change from one to the next. So let's look at part A, for example. So from 7 and 11 plus 4, 11 to 15 plus 4, 15 to 19 plus 4. So it looks like the pattern for part A is you just add 4 to every term. Part B, from 2 to negative 3, that's negative 5. From negative 3 to negative 8, that's also negative 5. And then from negative 8 to negative 13, that's also negative 5. So it looks like for part B, all you do is you just subtract 5 every single time. For C, it might be a little bit trickier to see what kind of pattern there is because we're working with fractions. But if it helps, usually with fractions, one easy technique to use or strategy to use to more easily see a pattern is to write all the fractions in terms of the same denominator. Okay, so here we can see here we have a 5/4, here we have a 7/4. So let's try to rewrite all these fractions so they have a 4 as a denominator. So 1, for example, is the same thing as 4/4. And 3/2, on the other hand, is the same thing as 6/4. So a strategy that can be helpful whenever working with fractions, sequences that have fractions in them. So now it might be a little bit easier to see what kind of pattern we have. We have 4/4, 5/4, 6/4, 7/4. So it looks like we're adding 1/4 every single time. So add 1/4 every single time. So, well, what do they have in common? Each of these sequences, you're always adding or subtracting the same number. Here you're always adding 4, here you're always subtracting 5, and here you're always adding 1/4. Okay? So, let's try to determine some explicit formulas for each of these sequences. Okay, so key here. Okay, this is key. We're adding 4 every single time. Adding 4 every single time. So this actually tells us that our formula is linear, okay? Whenever you have a difference that is the same between each term, that means you have a linear formula or linear equation. So the same thing happens with B, and the same thing happens with C, okay? So whenever your differences are the same, so here our difference is always 4, here our difference is always negative 5, and here our difference is always 1/4. That means your formula is going to be linear. So it just so happens these are the formulas that you end up with. So for part A, you end up with a sub n is equal to 4n plus 3. For part B, we end up with b sub n is equal to negative 5n plus 7. Wait, I got to make sure I get this right. Plus 7, yeah, plus 7. And then for c, we end up with c sub n is equal to 1/4 n plus 3/4. Okay? So those are the three explicit formulas. Now, you'll notice here, you might notice some things here. So once again, for part A, we said we were always adding 4. Well, look at what I ended up with. I ended up with a 4n as our explicit formula. Here we always said we were subtracting 5. Well, there's a negative 5 there, negative 5n. And then for part C, we said we were always adding 1/4. 1/4 n. So remember, a linear equation, going back to algebra 1, a linear equation typically has this form, y equals mx plus b, right? Or that is one form, we call the slope-intercept form, one form of a linear equation you should have learned back in algebra 1. So in this case, right, so instead of x's, we have n's, right? In this case, you'll see that there is some something going on here where whatever our difference is, so this was always plus 4, this was always minus 5, this was always plus 1/4, whatever our difference is looks like it corresponds to what the slope of our linear equation is. And on the flip side, the b value, which if you remember back to algebra 1, that's your y-intercept, that always corresponds to, well, that one might not seem as obvious. What does that correspond to? Well, it actually corresponds to the term before the first term. So for example, we have 7, right? Well, what would be, if we did this pattern backwards, what would be the number before 7? Well, let's see, 19, 15, 11, 7. So that means the one before should be 3, because I would subtract 4, right, to go backwards. So that is where that plus 3 came from. And then for part B, right, so let's see, negative 13, negative 8, negative 3, 2. So that means the one before that would be 7, right, if we went backwards. So instead of subtracting 5, we would add 5 to go backwards. And then the same thing happens with C as well. What would be the term before 1? Well, 1 was 4 over 4. So if we went backwards, so it would be 7/4, 6/4, 5/4, 4/4, 3/4. And that's how we get our b value in our linear equation. All right. So hopefully you're starting to notice some patterns here in terms of where these numbers are actually coming from. All right. So observations. We already talked about it. We said that all the sequences either added or subtracted by the same number every single time, right? Or it had a common difference. In other words, the difference between terms was always the same, right? So the difference between terms was always the same. So difference between terms always the same. It's probably a more appropriate way to say it this way as opposed to that way. And then we talked about generalizations, right? The m, or slope, quote unquote, was your difference. And then that b value, quote unquote, if you're thinking of your formula is y equals mx plus b, was your zero term. So the term before the first term. So term before first term. Okay. So let's make it a little bit more formal. Let's make it a little bit more official. So an arithmetic sequence. So an arithmetic sequence is a sequence whose consecutive terms have a common difference. That is what we call an arithmetic sequence. So those three examples that we just looked at, we just said, right, the differences was always the same, right? The first one was always plus 4, the second one was always minus 5, the third one was always plus 1/4. To go from one term to the other, those three examples were all arithmetic sequences. So in other words, if the difference between each term is the same, right? I forgot what the, 711, okay. So if the difference between each term is the same, right? That was the first example from example 1, 7 to 11. That's plus 4. 11 to 15, that's plus 4. 15 to 19, that's plus 4. That's how you know you have an arithmetic sequence in front of you. Okay? That's how you know you have an arithmetic sequence in front of you. Now, really quickly, if it's tricky for you to determine what the difference is, just know that an easy way to determine the difference is you take any two consecutive terms. So, for example, let's say we took 7 and 11. If you want to find the difference between the two, you simply find the difference between those two terms. So you literally just do 11 minus 7 is equal to 4. Right? That's how you would calculate what the difference is. If you're struggling to see that right off the bat that it is plus 4, that's how you can easily determine. Just take any two consecutive terms and then just subtract them from each other, and you would get what the difference is. Okay. Now let's look at the formula. So the nth term of an arithmetic sequence, has the form a sub n is equal to dn plus c. So a sub n is equal to dn plus c. So hopefully you can see some similarities between this and that slope-intercept form that you guys learned about in Algebra 1, right? We have a variable x, in this case we have n instead, and then we have m, instead of m we have d, and then b in place of c, right? So this is a linear formula. That's basically an arithmetic sequence. An arithmetic sequence is a linear pattern, a linear formula. So really quickly, and we kind of touched upon this earlier, d is the difference, the common difference. So whatever your common difference is, whether it's plus 4, minus 5, plus 1/4, that is going to be your d value, or your slope, going back to Algebra 1. And then the c value, like I told you, the c value is the term before the first term. All right? So another way to think of the c value is the zero term, in other words, or like I said, the term before the first term. So another way to think about it is you take your difference and you subtract it from the first term, right? You take your difference and you subtract it from the first term. That's another way you can think of it as your c value. So once again, kind of think of it as your y-intercept. That's another way to connecting back to Algebra 1. So that is what an arithmetic sequence will look like. Okay, like I said, it will be a linear equation. There's no squares, there's no square roots, there's no cubes, no. It's just a linear equation. Okay? So let's look at an example. Example 2. Find a formula for the nth term of the arithmetic sequence whose common difference is 3 and whose first term is 2. All right? Oh, so they gave us a common difference already, and they told us our first term is 2. So once again, common difference is 3. So they already told us our d value, and then they told us that our first term is 2. So the first term is 2. Well, remember, to find the nth term, so that means they're asking us for a formula, okay? Whenever they're asking us for the nth term, they're asking us for an explicit formula for the sequence. So we have a sub n is equal to dn plus c. That was the formula from the previous slide, right? That is the explicit formula for an arithmetic sequence. So we just said we know the d value is 3. So we have a sub n is equal to 3n plus c. So we still have to figure out what that c value is. Well, remember in the previous slide, there's two ways to think about it. Either you can think of it as the zero term. So if the first term is 2 and the difference is 3, right? If the first term is 2 and the difference is 3, well, that means the second term would be 5, the third term would be 8, so on and so forth. Well, what about if we went backwards, though? If we went backwards, the zero term, quote unquote, would be -1, right? If the common difference is always 3, the previous term before 2 would be -1, okay? So that's one way to figure that out, to figure out what C is equal to. Okay, or another way, as I explained in the previous slide, is we could also just do A sub 1. I'm sorry. We could also just do C is equal to A sub 1 minus D. Well, A sub 1 is 2. The first term is 2. And then the difference is 3. So that means C is negative 1. So we could have also done it that way. Okay. Ta-da! There's your explicit formula for this arithmetic sequence. Explicit, just to be specific. I forgot to include that in the directions, the explicit formula, including this slide. This should say the explicit formula for the nth term. So let me just add that. The explicit formula for the, there you go. All right. Well, let's pretend this example was different. Instead of the example telling us that the common difference is 3 and the first term is 2, what about if we had this instead? What about if we actually had the sequence itself? So 2, 5, 8, 11, Okay, let's say if that was given to us and they asked us to find the nth term of the arithmetic sequence or the explicit formula. Well, in this case, we would have to find the difference ourselves, right? We would have to actually do the math. So let's see, the difference between 2 and 5 is 3, because I know 5 minus 2 is 3. And then the same thing goes for 5 to 8, because 8 minus 5 is 3. And then 8 to 11, because 11 minus 8 is also 3. So at that point, that's how we would know the common difference is 3. And then we can basically follow the same process we did before to find what that C value was. Okay. So the rest is for you to try it on your own. So example 3, and you'll find this on Desmos. Example 3 is the problems that you want to do on your own. So make sure you read the directions carefully. Not all these sequences will be arithmetic. You're going to have to determine how they're arithmetic, and we covered that in our lesson for today, how you determine a sequence is arithmetic or not. And then if it is arithmetic, then I tell you to write an explicit and recursive formula, If it's not arithmetic, then you just leave it alone. Okay, so if it's not arithmetic, you just leave it alone. Okay, and then here's C and D. Okay, so once again, these problems should be on Desmos, so you can just complete them there. If they are not on Desmos, then obviously you can just do them on a separate sheet of paper and upload them from there as usual. Otherwise, I hope this lesson went well. If you have any questions, as usual, let me know. Reach out to me through whatever channels you feel most comfortable with. But otherwise, I hope you all stay safe, and I hope you enjoy the rest of your day.